In this video, we are going to be examining an important concept of basic algebra, which is a binomial theorem. So basically, this topic has to do with the relationship between two expressions connected by addition or by subtraction, and what happens when you try to expand it beyond the way it is. That is, if you have a plus b to power of n, where n could be any integer, it could be 0, 1, 2, 3, 4, 5, 6, and so on. So basically, that is what the idea of what I'm about to discuss in this video is all about. Okay, so let's say you're trying to expand the following expressions. Let's say you're trying to expand alpha plus gamma to the power of 0, alpha plus gamma to the power of 1, to the power of 2, to the power of 3, 4, and to the power of 5. From our understanding of indices, we know that when you raise something of such to the power of 0, you have 1. And when you take alpha plus gamma to the power of 1, you still have alpha plus gamma. Alpha plus gamma to the power of 2, from our understanding of expansion, alpha plus gamma squared is equal to alpha plus gamma times alpha plus gamma. So we do alpha squared plus alpha gamma plus alpha gamma plus gamma squared. Alpha squared plus 2 alpha gamma plus gamma squared. So this becomes alpha squared plus 2 alpha gamma plus gamma squared. Alpha plus gamma to the power of 3 is just taking alpha plus gamma and then you're multiplying that by alpha plus gamma to the power of 2. And we've previously obtained this as this. So we just do alpha plus gamma to multiply alpha squared plus 2 alpha gamma plus gamma squared. When you multiply, you have alpha cube plus 2 alpha squared gamma plus alpha gamma squared plus alpha squared gamma plus 2 alpha gamma squared plus gamma cube. When we collect the like terms, this is alpha squared gamma, this is alpha squared gamma. So we have 2 of them here, we have 1 of them here. So we have 3 alpha squared gamma plus 3 alpha gamma squared plus gamma cube. So when we come back here, we do alpha gamma plus 3 alpha squared gamma plus 3 alpha gamma squared plus gamma to the power of 3. If you go on with this process for alpha plus gamma to the power of 4, you're going to obtain alpha to the power of 4 plus 4 alpha cube gamma plus 6 alpha squared gamma squared plus 4 alpha gamma cube plus gamma to the power of 4. Lastly, if you do the same for alpha plus gamma to the power of 5, you're going to have alpha to the power of 5 plus 5 alpha to the power of 4 gamma plus 10 alpha cube gamma squared plus 10 alpha squared gamma cube plus 5 alpha gamma to the power of 4 plus gamma to the power of 5. If we take a moment to look at this expansion, there is a particular pattern, a kind of hidden, but we can bring it out. Now this pattern is going to be such that we're going to examine, we're going to extract the coefficients of all the algebraic terms, and for the first one where you have the constant term, we're going to put that out as well. So we have 1, the coefficient of alpha here is 1, and that of gamma is 1. Now for the third one, we have the coefficient of alpha squared is 1, the coefficient of alpha gamma is 2, and the coefficient of gamma squared is 1. So we will go on with the process. We have 1, 3, 3, 1. This is 1, 4, 6, 4, 1. This is 1, 5, 10, 10, 5, and 1. Now, this is the pattern I was talking about earlier on. And in this pattern, we notice a couple of things. First, each pattern begins and ends with 1. So we can call this more like an isolated case, but we can technically say that this begins and ends with 1 since it's just 1. And if you look at every other expressions or every other numbers that we've derived, we're going to say that it starts with 1, ends with 1, 1, 1. The first, the last, the first, the last, the first, and the last. Again, we're also going to notice that the pattern is kind of symmetric. That is, we have a kind of mirror image. There is a kind of mirror image. Starting with this, we're going to see that we have 1 on this side and 1 on this side along this line, imaginary line that I drew. And for the other case, we can see that the symmetry is about this middle term, which is 2. And for this, if I draw this imaginary line, we're going to see that we have 3, 1, and here we have 3, 1. And in this case as well, it is symmetric about this middle term. So 4, 1, and here again is 4, 1. And for the fifth, we're going to see that if I draw this line, this is 10, 5, 1, and along this side we have 10, 5, 1. And you will notice that in certain cases, we are not having it exactly. It's either it is direct symmetry or it is symmetric around a particular number, like the case of 1, 2, 1, 1, 4, 6, 4, 1. Okay, we're going to see that it is symmetric about those numbers. So what is the actual thing to look out for here? We're going to notice that in this case, n is 0. Here, n is 1. N is 2. N is 3, 4, and n is 5. And taking a moment again to look at it, we're going to see that here, it's symmetric about a particular number. Here, it is symmetric about a particular number. And those two cases that we've seen are the cases where n is even. Okay, that is when n is 2 and n is 6. So which means that this case of being symmetric about a particular middle number only happens when n is even. Again, we notice that the second term and the second to the last term. Now this is quite visible when you have n is equal to 3 and above. Okay, when n is greater than or equal to 3. We're going to notice that this second term and the second to the last term are the same. The second term, second to the last term, the second term, and the second to the last term. They're identical. And in fact, not just that alone, we notice that these numbers are equivalent to the power of n. So we can see that n is equal to 3, and we notice by this pattern that the second to the last term and the second term, they're 3. The same thing goes with 4. The same thing goes with 5. And lastly, we also see that we can actually generate a next line. We can write the next line from the previous line. That is, we can generate for n equals to 6 by, don't forget, starting with 1, and it's also going to end with 1. And we can have the two adjacent numbers. That is 5 plus 1, then 10 plus 5, 10 plus 10, 5 plus 10, 15, 1 plus 5, 6, and then hence with 1. We can also do that for n is equal to 7. We'll go on. It starts with 1. 1 plus 6, 7. 15 plus 6, that is 21. 35. 21. 7 and 1. This pattern is what we refer to as the Pascal's triangle. As you can see, that it forms a kind of triangle from that point of view. Now we're going to be using this Pascal triangle to expand subsequent binomial expressions in the next chapter. Now we're going to be solving some problems using the Pascal's triangle. So the Pascal triangle is on the right hand side. We're going to be using that to solve the following problems. So we're asked to expand x plus 1 to power of 3. So we notice that x plus 1 to power of 3 follows the pattern alpha plus gamma to power of 3. So using this expansion, we can see that this is n is equal to 3. And this means we're going to be having alpha to power of 3 plus this 3, okay, alpha squared gamma. Now, as you proceed from the power of 3 to the next one, the power of alpha begins to reduce, right? And that of gamma begins to increase. Plus, then we pick the next 3. We do 3. Now we're going to have alpha to power of 2 again. It's going to reduce to alpha to power of 1. And that of gamma goes up to 2. And lastly, we have 1 here. That's going to be alpha goes to 0 now because it has been reduced, and this goes all the way up to 3. Now if you look at x plus 1, okay, we can call the x alpha, we can call 1 gamma. So when we substitute that in, we have x cubed plus 3x squared times gamma is 1 plus 3x times 1 squared plus gamma is 1 cube. So this becomes x to the power of 3 times 1. We have 3x squared 1 squared is 1. When you multiply that by 3x, we have 3x. And then plus 1. So that's it. The second one, we have x plus 2 to power 5. Again, if you use the alpha plus gamma to power 5, alpha starts with the power 5. Then we pick 5. Then the power of 5 reduces to the power of 4. And then gamma takes over. Plus, then we have 10. Then we do 10 alpha. It reduces to 3. And then this increases to 2. Plus, then we do 10 again. 10. Alpha goes down again to 2. Then gamma goes to 3. Plus, we have 5. Alpha goes to 1 as a power, and then gamma goes to 4. Then plus gamma to power 5. You would notice that as we move from the left to the right hand side, the sum of the powers remains 5. So here we have 5. Gamma is to the power of 1. 1 plus 4 is 5. Gamma is to the power of 2 plus 3, we have 5. It goes on like that, and it's all 5. And as we've said, that if this is alpha and this is gamma, then by replacement, remember, alpha is x, gamma is 2. So we do x to the power 5 plus 5 alpha, that's x to the power 4, multiplied by gamma is 2, plus 10 alpha again, x to the power of 3, gamma 2. Now we have 2 to the power of 2, plus 10 alpha x squared, gamma 2 to the power of 3, plus 5 alpha x gamma 2 to the power 4, plus gamma to the power 5. So this equals to x to the power 5. 2 times 5 is 10, so we have 10 x to the power 4 plus 10 x to the power of 3 times 4 plus 10x squared times 8 plus 5x times 16 plus 32. X to the power 5 plus 10x to the power 4 plus 40x to the power of 3 plus 80x to the power of 2 plus 80x plus 32. Now let's consider more instances. Let's say you're trying to do the same with 1 plus 2x to the power of 6. So we can take alpha as 1, gamma as 2x. And based on what we have here, alpha plus gamma to the power of 6 is going to be equal to alpha to the power of 6 plus 6 alpha to the power of 5 gamma plus 15 alpha to the power of 4 gamma to the power of 2 plus 20 alpha to the power of 3 gamma to the power of 3 plus 15 alpha to the power of 2 gamma to the power of 4 plus 6 alpha gamma to the power of 5 plus gamma to the power of 6. So we're going to carefully substitute these numbers into these expressions. alpha is 1, so we have 1 to the power of 6 plus 6 times 1 to the power of 5, gamma is 2x, so times 2x, plus 15, alpha is 1 to the power of 4, gamma 2x, 2x to the power of 5, sorry, to the power of 2, plus 20 times 1 to the power of 3, gamma, that is 2x to the power of 3, plus, I'm here, 15 times 1 squared times gamma, 2x to the power of 4, plus 6 times gamma is 1 again, sorry, alpha is 1 again, then gamma to the power of 5, plus more like that. Now 1 to the power of 6 is 1, plus 1 to the power of 5 is 1, times 6, we have 6.
It's 20 hours.
So, I beg your pardon. So we have 15 times 1, because 1 to the power of 4 is 1, times 4x to the power of 2, plus 20 times 1 cube is 20, times 2x to the power of 3 is 8x cube, plus 15 times 1 is 15, then 2x to the power of 4, that is 16x to the power of 4, plus 6 times 32x to the power of 5, plus 64x to the power of 6. Now when we simplify this, we have 1 plus 12x plus 60x squared plus 160 x to the power of x to the power of 3 plus 240 x to the power of 4 plus 192 x to the power of 5 plus 64 x to the power of 6. So that is that for 1 plus 2x to the power of 6. For the second one, 2 minus x to the power of 5, the process remains the same, but you have to be careful because now we have a negative coefficient of x. So what we have to do now is to rewrite the expression. We're going to rewrite 2 minus x as 2 plus negative x to the power of 5. And if you wish, you can call this alpha again, and you can call this gamma. So alpha is 2, gamma is negative x. So when you go back to your expression, this is our expression, this guy, for, okay, we have alpha plus gamma to the power of 5 equals alpha to the power of 5 plus 5 alpha to the power of 4 gamma plus 10 alpha to the power of 3 gamma squared plus right. Alpha is 2 to the power of 5 plus 5 times 2 to the power of 4 times gamma is negative x, okay, plus 10 times 2 to the power of 3 gamma squared minus x squared plus 10 alpha, that is 2 to the power of 2 gamma cube plus 5 times 2 times gamma to the power of 4 plus, that is gamma to the power of 5. So when we go on with this, we have 32 plus 5 times 16 times minus x plus 10 times 8 times minus x squared plus 10 times 4 times minus x to the power of 3 plus 10 times minus x to the power of 4, then plus minus x to the power of 5. So this becomes 32 plus 80 times minus x plus 80 again times, now we are squaring the negative x, so you're going to have x squared plus, here we have 40. Now you are raising negative x to the power of 3, which is an odd power, so you're going to have it to multiply minus x to the power of 3, then plus 10 x to the power of 4, the power is even, then plus minus x to the power of 5. Now this becomes 32 minus 80x plus 80x squared minus 40x to the power of 3 plus 10x to the power of 4 minus x to the power of 5. So that is that for the expansion. The last question for this session is to do this. So we'll write this as 2p plus negative 3q all to the power of 4. And the Pascal triangle numbers for a power of 4 are 1, 4, 6, 4, and 1. So we decide to take this as alpha again, and this as gamma, and we do alpha plus gamma to the power of 4. We're going to be having right. So let's plug in the values. Alpha is 2p, so 2p all to the power of 4 plus 4 times 2p all to the power of 3. Now gamma is minus 3q plus 6 alpha squared 2p squared gamma squared negative 3q all squared. Okay, now plus 4, we are here right now, times 2p gamma cube, that is minus 3q all to the power of 3, and lastly plus minus 3q all to the power of 4. Now 2p to the power of 4 is going to give us 16p to the power of 4 plus we have 4, 2p to the power of 3 is 8p cube, and then let's multiply that by this, plus 6 times 2 to the power of 2 is 4, and then we have p squared. Now we multiply that by minus 3q squared is going to give us 9q squared. As we've all known that when you square a negative, it becomes positive. 4 times 2p, and this is going to give us minus 27q to the power of 3, and of course this is going to be 3q whole to the power of 4. So we do 16p to the power of 4. Now we have a negative here to multiply positive here, that gives negative. 4 times 8, 32, 32 times 9, that is 96 p cube, then q, plus 6 times 4, that is 24. 24 times 9 is going to give us 216 p squared q squared. Here again we have a negative multiplying a positive, that gives negative. 4 times 4 times 2 is 8. 8 times 27, that is again 216 p q to the power of 3, plus 81 q to the power of 4. So basically this is how to use the Pascal's triangle to expand binomial expressions of your choice. So in the next session we're going to look at the last form of binomial expressions you can use the Pascal triangle to expand. Finally, we're going to be using the Pascal's triangle to expand the two expressions. So the process remains the same, you just have to be more careful in this case. So we have x plus 1 over x to the power of 4. So we can pick the first expression here for our expansion. So we take x as alpha and 1 over x as gamma. So x to the power of 4, that is gamma to the power of 4, then plus 4 alpha power of 3 gamma, plus 6 alpha to the power of 2 gamma to the power of 2, plus 4 alpha gamma to the power of 3 plus gamma to the power of 4. So this becomes x to the power of 4 plus 4x squared, as this law of indices, plus this is 6x squared times 1 over x squared plus 4x times 1 over x cubed plus 1 over x to the power of 4. Now this is equals to x to the power of 4 plus 4x squared plus 6 plus 4 over x squared plus 1 over x to the power of 4. And that is that. For the second one, we have 1 plus x minus x squared whole to the power of 3. So we have to rewrite this as 1 plus x minus x squared whole to the power of 3, so that it follows the standard we've been using. So we're going to call this alpha again, we're going to call this gamma. So I'm using this expression alpha cube 1 cube plus 3 alpha squared, then gamma, plus 3 alpha gamma squared plus gamma cube. 1 cube is 1 plus 1 squared is 1 times 3, you have 3 all squared plus all to the power of 3. Now we are faced with the second challenge of expanding the third term and the fourth term. So we can decide, it depends, you can factorize, right? Or you can just go on with the expansion. So I'm going to go on with the expansion. Okay, 1 plus, I open this bracket, I have 3x minus 3x squared plus 3. Now this is not actually a large expression, so we can write it as this, right? So x times x is x squared, and x times minus x squared is going to give us minus x cubed. Then we have minus x cubed plus x to the power 4 plus, now we can use the binomial, the Pascal's triangle again to expand this. Remember that the Pascal's triangle for this is 1 3 3 1, so we can still use this as alpha and we can do this as gamma. So carefully, okay, we do, okay, alpha to the power of 3, that is x to the power of 3 plus 3 x to the power of 2. Now gamma begins to come up, minus x squared. Okay, now going on, we have plus 3. Okay, alpha goes down to 1 now, and gamma increases by a power of 2, all squared rather, and then this becomes minus x squared all to the power of 3. Then I close that. Now this equals to 1 plus 3x minus 3x squared plus 3 times x squared minus 2x to the power of 3 plus x to the power of 4. And here we have x to the power of 3 minus plus, that's minus 3x to the power of 4, and here we have minus x squared, that's x to the power of 4. When you multiply that by 3, you have x to the power of 5, and here we have minus x squared to the power of 3, that's going to be minus x to the power of 6. So we write out the whole expression and then we collect the like terms. 1 plus 3x minus 3x squared plus 3x squared minus 6x to the power of 3 plus 3x to the power of 4 plus x to the power of 3 minus 3x to the power of 4 plus 3x to the power of 5 minus x to the power of 6. So let's do what is needed to be done. There are no other constants, so we pick 1. No other x to the power of 1, so we just write 3x. Now let's check x to the power of 2. This and this automatically cancels out and we don't have any more. Okay, so we just go on to the power of 3. So we have minus 6x to the power of 3 and x to the power of 3. So this becomes minus 5x to the power of 3. Now let's go to the power of 4. This is to the power of 4. This is to the power of 4. and they are equal, so they cancel out. Plus 3x to the power of 5 minus x to the power of 6.